In this lesson, we're going to dive into measuring angles. We're going to talk about how we can measure angles and then a postulate related to adding angle measurements together. We're also going to talk a little bit about classifying angles in this lesson as well. All right, first of all, there is a tool that you can use to measure angles. Everybody should have one for geometry. That is known as a protractor. A protractor measures angles in degrees. Wait, what is a degree? Well, a degree is simply a measure that's equal to 1/360th of a circle. So we define a circle as being 360 degrees all the way around, and by comparing our angle number of degrees to a circle's number of degrees, we get a pretty good sense of how big our angle is, whether it's a complete circle, a half circle, less than a quarter of a circle, more than a quarter of a circle. By comparing, basically all a protractor does, it compares angles to a circle, and it tells us how much of the circle an angle takes up. All right, that brings us to our first postulate for this lesson, the protractor postulate. And I'm just going to say both the protractor postulate and the ruler postulate are super confusing. Okay, the wording on these is complicated. There's lots of parts you have to keep in your brain at the same time. If you get them, that's great. If these aren't making sense to you, it's enough to understand that these postulates are basically just saying that these tools exist and they work. So the ruler postulate says that rulers exist, they have scales on them, and they work to measure lengths. This is saying that protractors exist, and they have scales on them that measure the degrees of an angle, and they work to measure the degrees of an angle. That's basically what the protractor postulate says. We are going to go into it in depth, but if you feel yourself getting lost, don't worry about it too much. The protractor postulate itself isn't that important. It's understanding that protractors work and how protractors work that's important. All right, so notice that I have line PR at the base of my protractor. P passes through 0, R passes through 180. Then given a point X on PR, consider rays XP and XR as well as all other rays that can be drawn within X, with X as an endpoint on one side of PR. So A is an example of a line that has X on an endpoint on the side of PR. AX and BX is another example. BX has X as an endpoint on one side of PR. Okay, and you can imagine there's an infinite number of rays that I could draw all the way around that semicircle there. These rays can be paired with real numbers from 0 to 180 such that XP is paired with 0. Notice that XP crosses 0. XR is paired with 180. And then we could pair any other ray with a real number that's on the protractor all the way around. So XA gets paired with a number C, XB gets paired with a number D, and then if we want to know the measure between A and B, we just find C minus D and then take the absolute value. So for example, here I see that A is at 30 degrees, B is at 90 degrees. So if I do 30 minus 90, that gives me negative 60. And then I have to take the absolute value. The angle measure of BXA is 60 degrees. So I could just write a little 60 degrees in here because I know that this is a 60 degree angle. That's all it's doing. If you take one angle measure minus the other angle measure. Now here's the thing. Most human beings, when they use a protractor, instead of just arbitrarily orienting the protractor according to the page, what you usually do is put the protractor so that its bottom line is on one of your rays that you're measuring for your angle. So notice, and I'm going to struggle to line this up exactly right here, but notice that this protractor, when I angle it so that its bottom is right along ray A, it still reads 60 degrees, and now I don't have to do that extra subtraction step. Hey, one other thing about using a protractor, and I just want to point out, in your book, in the examples, they have a protractor that's wrong, and they use it wrong, and they should be ashamed for doing that. Now, notice what we're doing when I use a protractor to measure an angle. I'm always putting this little crisscross of lines at the bottom on the vertex of the angle. It has to be on the vertex of the angle, and then I'm making it so that one of the lines of my angle passes through 0, okay? And then I could read the angle measure up to where the other line is. But the key is that you have to be sure to line up your protractor so that wherever these two little crisscross lines crisscross, that happens at the vertex of the angle. In your book, there's crisscross lines on the protractor, but they're in the wrong spot for some reason on that protractor that's drawn there. Because when you put the crisscross lines at the vertex of your angle, you should notice that the bottom line of your angle passes through 0. If you did that in the protractor as pictured in your textbook, it would pass somewhere below 0, so it's just not right. Theirs, they try to line up with this horizontal part of the semicircle inside the protractor, which would work. It's just they wouldn't have the crisscross lines drawn then. So just so you know, you do need to, you'll have crisscross lines like this, like a target on every single protractor, and you have to put that target on the vertex. And then you can use the protractor postulate to figure out what the measure of your angle is. All right, let's talk about some classifications of angles. This angle AXR is an angle that's less than 90 degrees. So AXR, we would say, is an acute angle, an angle measure between 0 and 90 degrees. An acute angle is basically, what we're saying is it's smaller than a 90-degree angle. An obtuse angle, just the opposite. The angle PXA would be an obtuse angle, measures between 90 and 180. In fact, PXA would be a 150-degree angle according to this protractor. A right angle is an angle that measures exactly 90 degrees. BXP or BXR would be considered right angles that measure exactly 90. And then finally, a straight angle measures 180 degrees. It's a line. A straight angle is a line. PXR would be an example of a straight angle in my drawing. All right, moving on. Let's talk about the angle addition postulate. Here's another one that has a lot of language specific to the angles that's being set up, and it's a little bit heavy to understand, but I think you'll get it. So I want you to consider angle ABC. Look at angle ABC at the bottom of the page there. ABC, okay? And now look at point D. If point D is in the interior of ABC, then the measurement of angle ABC is equal to the measurement of ABD plus the measurement of DBC. Do you see how we're just splitting the angle into two parts? ABD and DBC. And I can get the whole angle by adding the sum of the parts. This is just like the segment addition that we did in a previous lesson, except in this case we're dealing with angles instead. All right, and then just a few more terms that we need to know. The term bisect means that you're dividing a figure into two equal parts. We could bisect a line by putting the midpoint on that line, and the midpoint separates the, and I should say line segment. We can bisect a line segment by putting a midpoint on the line segment, and then that midpoint separates it into two equal parts. Well, we do the same thing with an angle. We call an angle bisector a ray that divides an angle into two equal parts. And I measured it to make ABD and DBC the same measure in the angle right over here. So because ABD, the measure of angle ABD equals the measure of angle DBC, the ray BD is an angle bisector. By the way, just want to point out up here and down here, I forgot to mention that whenever we write M of angle AB, so the measure of angle ABC, the measure of angle ABD, we're talking about as a value associated with the measure of the angle. Okay, so we're not talking about the angle as a figure anymore. Then we're talking about the number, the measure of the angle. And that's what we're talking about with an angle bisector too. Congruent angles are angles that have the same measures. We would say if BD is the angle bisector of ABC, then ABD is congruent to DBC. We would use the same congruency symbol that we've been using in previous lessons as well. And lastly, I'm going to talk about arc marks. Arc marks show congruent angles. Right now I have an arc mark on ABD and an arc mark on DBC, and they perfectly match each other to show that those two angles are congruent. Both of them are a single line arc mark. If I wanted to, I could drag in another arc mark to make a double line arc mark. Let's just do that. So here, I'm no longer saying that ABD is congruent to DBC because notice they have different arc marks. Well, one has 2 and one has 1. I could also, if I wanted to, put little hash marks on the arc mark to show that these are similar too. Anything you do to make the two arcs look similar. But now I know that ray BD is an angle bisector, so I know that ABD is congruent to DBC. So I'm just going to show that congruency by putting an arc mark up here as well. Let's see if that's good. Yep. So because I have 2 of my arcs on each angle and they match each other, that means that they are congruent. They're the same. All right, that's it. Now we know a lot more about angles, and the next thing we're going to do is work some practice problems related to angles.